Hi, I'm John Froelich, a professor in computer science, and I study sidewalks. Sidewalks are critical public infrastructure. They help connect our cities. They allow us to go to work, to school, to visit the doctor, to take public transit, and they support local commerce and recreation. For people with disabilities, sidewalks play an even more crucial role in supporting independence, quality of life, and overall physical activity. The problem is, city streets, sidewalks, and businesses are not accessible. I'm showing a famous picture archived at the National Museum of American History, taken during the rise of the disability rights movement, which shows a wheelchair user stuck at the edge of a curb. Take note, the built environment was designed inaccessibly, excluding the usage of the sidewalk. But it's not just a lack of curb ramps, as shown here in New York. It's also physical barriers like poles or fire hydrants. Here we have a curb ramp, but it's blocked by a pole. There's also abruptly ending sidewalks where somehow the sidewalk just runs out. Or we might have surface problems due to weathering, root growth, or other degradations. And in the worst case, we have a scene like this: multiple physical impediments and poor sidewalk design leading to unsafe conditions and inaccessibility. And these have dramatic, serious consequences, as captured by one of our interviewees.
When I go to school in the morning, I don't take the sidewalks. I actually take the street, and they shout at me from their cars. They're like, "Get off the road." And it's like, I can't actually use the sidewalk.
As the UN's New Urban Agenda states, this designed inaccessibility contributes to and further reinforces systemic inequalities in economic opportunity and access to basic health and educational services for people with disabilities. But the problem is not just a lack of accessible infrastructure, it's also a lack of data. The National Council on Disability notes that there is no comprehensive information on the degree to which sidewalks are accessible in cities. And my close collaborator, University of Illinois Chicago professor Yochai Eisenberg, conducted a systematic evaluation of ADA transition plans in the U.S. They found of 401 government entities studied, only 13% had the required ADA transition plans for sidewalks, and just 7 of the 54 plans met all required criteria. So my group is pursuing a twofold solution. First, to develop scalable data collection methods that mine massive repositories of online map imagery, like satellite imagery or streetscape imagery that I'm showing here, using a combination of crowdsourcing and machine learning. And second, to create new urban analytics not previously possible. For example, in a beta version of our tool Access Score, which I'm showing here, users can get an at-a-glance custom view of the sidewalk accessibility in their city. Our overarching goal is to map, assess, and visualize every sidewalk in the world by creating scalable human AI crowd techniques. And we have been long working in this space. Each paper here represents a scientific publication advancing work in this area. Research that has significantly relied on community engagement and community science through a tool called Project Sidewalk. Project Sidewalk is an open-source crowdsourcing tool for sidewalks, available at projectsidewalk.org. We invite you to try it out. And we're proud to be featured on SciStarter, which is a platform for finding and contributing to community science. You can even earn credit in the SciStarter dashboard for participation. So Project Sidewalk combines online map imagery, remote crowdsourcing interfaces for labeling and validation, and machine learning to scalably map and assess sidewalks. And there's a variety of key outcomes. So working with our partners, Project Sidewalk is being used to improve urban planning, build new interactive visual analytics, and improve government accountability. So let's take a look at how to use Project Sidewalk. Project Sidewalk is built sort of like a first-person video game. It has 2 game missions. The first is exploring and labeling the sidewalk environment, and the second is validating and correcting other people's labels. So let's take a look at labeling. Here, users find, label, and rate problems. The user finds and labels a surface problem in this video, and then turns to the other side of the road and finds and labels missing sidewalks. The labeling interface is broken down into 4 parts. We have 7 label types at the top, a sidebar with mission statistics, a mission map that guides you on where to go in the world, and then the Google Street View pane for labeling. I want you to imagine using Project Sidewalk. What do you see in this image? Well, hopefully you've identified this tripping hazard, an uplift, So you would click surface problem, you would drag that label over to the identified area, and then you would add severity, comments, and potentially tags. Here's another example. What do you see? Well, some of you may have identified that whole obstacle right there in this fairly narrow sidewalk, and this is from our deployment in Mexico. So this would be an impassable barrier to someone in a wheelchair, and so we would mark 5 for impassable and also pull for the tag. And each label type has a variety of different types of tags, so we can get very rich information on the type of accessibility obstacle. Each of these labels are also geolocated, enabling new types of visual analytics of sidewalk problems. Here I'm showing over 260,000 labels that we collected from our users in Washington, D.C. And critically and importantly, you don't actually have to be located in the city that you're evaluating. So for example, here is a child in Germany labeling a neighborhood in Mexico City. Now remember I talked about the other game mission, which is validation. So we want to try to improve our data quality as much as possible. And here you're shown other people's labels, and you're just asked, is this an obstacle? Is this a surface problem? And you can mark agree, disagree, or not sure. So again, imagine using the interface. Do you see where the arrow is pointing to a pole and a bike on the sidewalk? Is this an obstacle? If you agree, you would mark agree. Here's another example. Is this a missing curb ramp? We have a crosswalk, but notice at the end of that crosswalk, we actually don't have a curb ramp. So yes, you would mark this is a missing curb ramp. How about this? Here we have a driveway in a suburban neighborhood. Well, in this case, and this is a common mistake, especially for novice users, a driveway is not a curb ramp. While wheelchair users might use it to get down to the roadway, it's often a last resort, and it's not ADA regulated. How about this one? This pole is not an obstacle. There's plenty of room to maneuver around it, and so you would mark disagree. And finally, how about this surface problem? This is a very significant uplifted panel, which would create a tripping hazard or an impassable barrier for somebody in a wheelchair. So we would mark it agree. We also try to make Project Sidewalk fun and educational. So we use game design strategies to reward achievements, to earn badges and divide work. And we also have a leaderboard, which has been particularly successful for some of our after-school and community deployments. So let's talk about some of these deployments right now. We are currently working with our local community groups and government partners. We deployed Project Sidewalk in 20 cities across 4 continents in 7 countries, including the US, Mexico, Ecuador, Netherlands, Switzerland, and New Zealand, with more to come. Project Sidewalk is also natively translated into Dutch, Mandarin, Spanish, and German. In total, Project Sidewalk users have contributed over 1.5 million data points. And the single most important ingredient to all of our deployments is you and our partners. In each deployment city, we establish and work closely with community partners to identify shared goals. And most of this growth is organic, receiving emails from people that want to deploy in their communities and care deeply about improving their cities for people with disabilities. We can deploy anywhere there is a Google map. In Amsterdam, for example, we work directly with the city, government, and an international disability organization called World Enabled. In Mexico City, we worked closely with a pedestrian rights organization called Liga Peatonal and the National University. In Newberg, Oregon, we worked with 2 disability advocates and the city of Newberg itself. The city added Project Sidewalk to their official public works page, which this screenshot shows. I'm showing now a top-down map of all the data collected. Over 230 users participated, completely mapping and assessing all of Newberg, Oregon's streets, 116 miles. You can start to see different kinds of visual patterns. For example, a lot of missing sidewalks around the periphery of the city. And then surface problems and missing curb ramps in the city core. As a result of our data, the Newberg City Council established a new sidewalk renovation program in the region, including the authorization of $50,000 for immediate sidewalk repairs on city property, and established a sidewalk accessibility grant program to help homeowners fix sidewalks outside their homes. And then lastly, we recently completed a deployment in Oradell, New Jersey, working with local Girl Scouts, a hospital, and a local disability advocacy group. Here again, I'm showing a color-coded map of the collected data. 225 community users contributed over 12,000 labels and 19,000 validations. And what's interesting about Oradell is if you just look at where there are surface problems, and then you look at where there are missing sidewalks, you end up with a complete city grid, which means that where there are sidewalks, they're not in good quality. And because our users also tag things, we can sort of dig into some of these different kinds of patterns. Most of the problems in Oradell, New Jersey happen to be height differences or uplifts. So here are some of those examples that are marked as high severity. So they have root growth that's pushed up a lot of their sidewalk panels, creating this inaccessible pathway. But perhaps the most interesting part of this project was not the data collected in the analytics, but the service learning component. Local Girl Scout troops helped use Project Sidewalk throughout the timeline of the project, including presenting their findings to the City Council and doing all of the analysis. We have just launched a new website called accessiblecommunities.org, which helps interested parties understand what they can do to improve their sidewalks and transportation systems for people with disabilities, and also provides service learning curriculum and examples for educators and workforce developer professionals. All of our data and tools are open source, so others can build on our work. Our code is hosted on a platform called GitHub, and our data is provided by APIs at projectsidewalk.org/API. This has allowed others to build on our work. For example, Barbara Moreno built an interactive tool visualizing sidewalk accessibility in DC, which received local press. Microsoft's AI for Good Lab has been using our data to train new computer vision models for urban accessibility. And most recently, scientists at Simon Fraser University and the city of Burnaby are using Project Sidewalk to study the relationship between the built environment and outdoor activities for older adults. You might be asking yourself, well, where does AI come in? Recall that we have over 1.5 million crowdsourced data points. That's a huge opportunity for us to train machine learning algorithms. So we feed this manually labeled data into our CV models, and we're specifically interested in how can we harness all of this data to train machine learning algorithms to be more efficient and higher quality. Let me give you a few examples. Here's example performance from a state-of-the-art computer vision algorithm called YOLO V8, which is trained on Mapillary and Project Sidewalk data. You'll notice that the computer vision model, or CV model, is automatically detecting sidewalk-related barriers such as signs, poles, but it's also making some mistakes. Here's another way that we're using computer vision, through a new prototype validation interface. Here, you can imagine having a human validate not just human labels, but also machine-contributed labels as well. We've also been experimenting with flipping our entire pipeline. What if we do AI-first assessments and then human validations? So that's exactly what this tool is doing, but here for bus stop accessibility. The AI algorithm is analyzing the bus stop, providing these labels automatically, and then a human is doing review and validation. With that, I wanted to thank you for your attention. I wanted to thank you to our sponsors, specifically the National Science Foundation, the Alfred P. Sloan Foundation, and PacTrans. And I wanted to end on a call to action, to join us. Together, let's transform the world's sidewalks at projectsidewalk.org.